Okay, so very happy to be here today. First time ever in South America for me, so I'm very excited. This talk is a research a team of two people, me and my co-speaker, but unfortunately he's not coming because he's too busy, so I'm here to represent the team. Okay, so this talks about finding zero days in embedded system using the latest advanced fuzzing technology named code coverage guided fuzzer. Okay, so a bit of myself. I'm working in Nanyang Technological University in Singapore, and I mostly do my research in low-level system stuff like operating system, virtual machine, binary analysis, and so on. And I happen to be the author and the maintainer of a few reversing projects. Capstone disassembler, unicorn emulator, and keystone assembler. Okay, so my co-speaker, Kaijan, he's working in JD, one of the biggest e-commerce company in China. He's an expert on hardware reversing, IoT security, and blockchain research. Okay, so a bit about what we present today. First of all, we take a look at in some background on coverage-guided fuzzer. And the idea is that we want to bring this technique to embedded system. So we want to build an embedded fuzzer using this guided fuzzer techniques. And to do this, we need to show many problems. One of them is that how to emulate the firmware. So we can build a fuzzer and run inside that. And we need some new dynamic binary instrumentation so we can fast own cap CPUs. And next, we show you how we build our guided fuzzer. And after that, if we have some time, we have some very simple demo, very quick demo. Okay, first of all, what's the fuzzing? The idea is very simple. Fuzzing is the automated software testing technique to find bugs. So the idea is that we feed some graph input data to the program that we want to test, the program we want to find bugs inside. And you can see here's a loop. We have a loop here. So we send the graph input data to the program that we want to find bugs inside. And when the program runs, we monitor the program to detect the violation. And okay, you can easily monitor for bugs like errors like crash or hang or memory leaking. And if we focus on exploitable bugs like memory corruption or information leaking, we can find vulnerabilities. So the idea is that on the fuzzer, because the program you want to find bugs inside usually has a very big, very huge code space, right? So the idea is that we want to generate the good input. So when the fuzzer runs, the fuzzer can find as much code as possible. Or in the other word, we want to maximize the code coverage to have the better chance to find bugs. So there are few types of fuzzer. Black box fuzzing and white box fuzzing are the first two types. So black box fuzzing is kind of very simple and dumb fuzzer. So the idea is that we feed the input into some random input into the fuzzer, and the fuzzer runs the program. And the fuzzer doesn't know how the program works inside, just send random input, and hopefully it crashes. So black box fuzzing is very easy to build, very easy to program, to maintain, but it's kind of dumb because it doesn't know how it works inside. So it doesn't know how to generate the good input to exercise a lot of code inside the program. So the next type of fuzzer is called white box fuzzer. So this one is unlike black box fuzzer. White box fuzzer, before it generates the input for the program, it tries to analyze the program to understand it, how it works inside, how it's structured, so it can generate the better input. So in theory, the idea of white box fuzzer is very nice. It should be, if we do this, we should have very smart fuzzer, right? But in theory, that's a theory, but in reality, it doesn't really work because white box fuzzer, they use some very complicated and heavy program analysis technique. So in fact, white box fuzzer is very slow, so it doesn't work well. So we come to the third type fuzzer is gray box fuzzer, which is something in between white and black. And the other name of gray box fuzzer is a coverage guided fuzzer. So yeah, this kind of fuzzer is they use the same concept, but you can see that when the fuzzer runs the program, it instruments it. So thanks to the instrumentation, the fuzzer knows what's going on, which code is already exercised. So in turn, it can generate a better input. So you can see that this kind of fuzzer is much smarter than the black box fuzzer because it knows how it works, how the program works inside. But it doesn't use heavy and very complicated program analysis technique like white box fuzzer. So you can see that it's proved to be very effective this way because guided fuzzer is very easy to use and very easy to set up, and actually it found a lot of bugs. And guided fuzzer become a trending in fuzzing technology. And one type of this kind of fuzzer is American fuzzy loop, or AFL. And in the last few years, AFL found a lot of bugs. Okay, so the idea is that in the last 2 years, I built some guided fuzzer based on AFL. But that guided fuzzer was only for powerful system, for PC. Now, what if we want to bring this fuzzer to run on the embedded system, which is very different from the powerful system like PC? So turn out that we have many issues. We want to bring this fuzzer to run on an embedded system. The first one is restricted. The embedded system, they are all very restricted. The second issue is that they are very close. And the last one is we do not have a lot of support for embedded system when you build this kind of fuzzer. Okay, so the first issue is restricted system. So you can see that in an embedded system like router or IP camera or so on, they do not provide you the built-in access, right? They do not give you the access to the embedded system. So that means you cannot come into the embedded system and build your own tools to build your own fuzzer. So it's very clear because inside all the embedded system, they do not provide you the compilers or any like development tools like debugger or any analysis tools. So that's the first issue. You cannot easily put your fuzzer or any development tools into an embedded system. The second issue is a closed system. So we can see that in many embedded systems, they do not provide a source code. So we do not have a source code. So what we have only is that we have the binary only, the firmware without any source code at all. So this is a big issue because on or most of the public guided fuzzer you can find in the public nowadays, they rely on the source code. You need a source code, and you compile the source code using some like special compiler. And this special compiler instrument program, and the fuzzer in turn runs this instrumented program inside the fuzzer. So you see that we need source code to compile the program, right? Actually, to be fair, there's some techniques to fuzz the binary only. For example, AFL, they support QEMU mode, so you can emulate the program in QEMU mode and run inside AFL. But actually, this technique is very slow, and there's many limitations, many programs that you cannot run in QEMU mode inside AFL. So the last issue is that most fuzzers, they are built for Intel chip only. So the reason is that once you have the program, you have the source code, right? Do you want to build this program to run on the embedded system? No. Because embedded systems are very poor in terms of performance. So usually you have source code, you compile this one to run on powerful system, which is PC, right? Which has a lot of memory, a lot of storage, and has very fast CPU. So you can see that most fuzzers, they are built for Intel only, but not for embedded system. Not for chips running on ARM, ARM64, MIPS, and PowerPC, and so on. So one clear example is that if we use some dynamic instrumentation to build the fuzzer, we rely on some like public DPI like pin or dynamo, right? But pin, for example, pin come from Intel. It supports CPU x86 chip only. It doesn't support other CPU. So no support for ARM, ARM64, MIPS, or PowerPC for pin. And it's the same thing for Dynamo module. Okay, so we see that you have many issues. We want to bring the guided fuzzer to embedded system. Okay, so we need to show many issues. The first one is how to build our fuzzer to run on embedded system. So we came up with one solution is just to emulate the firmware. So one thing you can see that coming from PC, we go to embedded system. Everything is scaled down. CPU is much slower. We have much less memory. We don't have like gigabyte memory on embedded system, but only typically you have like 16 or 32 megabyte. And of course, storage is much less. We don't have the terabyte hard disk on the embedded system. So, okay, you can see that the idea is that a very obvious idea is 1 to 5 bucks inside this embedded system. I buy that device, right? And we try to somehow inject our fuzzer or any analysis tool inside that embedded system. And actually, initially we bought some device like that on like that MDK bought on the screen. But it turned out that even if somehow we can try to inject our fuzzer into that device, it's very slow. You can run the fuzzer, but it's very slow. So, what's the solution? The idea is that now we want to 5 bucks inside this device. We come up with another solution. We try to get that firmware of the device and bring this firmware to a better performance system and try to 5 bucks in that. But we do not 5 bucks in the original device. So the first issue is that how to get the firmware. So there are many ways to get firmware. For example, you can take out the flash memory from the device and you extract firmware directly from the flash memory. And we get the firmware, right? The other way is that we can somehow extract the firmware from some APK, some Android application. For some reason, they have firmware inside. Or you can snip the traffic when the device is upgraded. The last solution is that many vendors, they provide the firmware on their website. So people can get it and upload and upgrade it. So yeah, we have many ways to get firmware of the device we want to 5 bucks in. The easy way is that with the firmware, we try to find the real device that supports that CPU. For example, you get the firmware of the MIPS device, MIPS in the system. We try to find a good board of MIPS, and we bring this firmware to run on that MIPS device, right? For the ARM firmware, you can buy a Raspberry Pi device and try to run this firmware on that Raspberry Pi. Same thing for ARM64, you can buy Raspberry Pi 3 and run the firmware on that. However, we found that this kind of solution is not very good. So one of the reasons is that our team has 2 people, right? We work actually we work remotely. We are not in the same place. So we do not want to buy the same device and send back and forth between us to work together. So we came up with another solution. How about we get the firmware but we do not run on the real device. We do not need to buy any device, but we try to emulate that into some virtual machine, right? So in this case, we do not need any device at all. So there are many advantages. If we have the firmware, you can emulate that in some virtual machine. You can add, because the virtual machine is owned by software emulator. So you can add as many core as you want. You can put 1 core, 2 core, 3 core, 4 core into that virtual machine, which we do not have in real device. You can add a lot of more RAMs compared to the original device. So for example, for ARM in the system, you can put up to like 0.5 GB memory into the virtual machine. And of course, you can put a lot more storage into the virtual machine. One more advantage is that you can scale up. So if you want to find bugs in this firmware, you can run many virtual machines of this firmware at the same time, and you can do like parallel fuzzer. So there are many advantages. So we decided to go this way. So okay, when we did this, we look into the past and to see how people solve this problem. So some people came up with some way. So given the firmware, they can put this firmware into like QEMU virtual machine, right? QEMU emulator, and they try to configure the QEMU emulator to run this firmware, so they can boot it up and run everything inside the QEMU virtual machine. However, we found that this doesn't work very well because we have many types in the system, right? And each emulator system has different kind of hardware. Now, if you want to bring this firmware into QEMU, QEMU need to be able to support all kind of hardware available in all those emulator systems. And actually, QEMU doesn't support many kind of device. So this kind of solution doesn't work well at all. So what did we do? So now we decided that we have the firmware. We try to emulate that in our virtual machine, right? But virtual machine doesn't support own kind of like firmware. So we thought, and we had some ideas. Usually, when we try to find bugs inside a firmware, we try to attack something that has big attack surface, right? And usually, firmware, the biggest attack surface in the firmware is that some service, some internet, some network service that are exposed to the network. For example, all the emulator system that we try to attack has web server running inside, right? So the idea is that we do not want to emulate on the firmware, but we just want to emulate that process that we try to find bugs inside, right? So in this case, for example, we want to find bug inside this firmware which has web server. We just try to emulate that web server only. So the idea is that once we got the firmware from somewhere, we extract the target binary, for example, HTTPD program from that firmware. We get it out and bring this target binary to our virtual machine. And we try to emulate that program in our virtual machine, and we attack it. That's it. So that's the whole idea behind this. So okay, we extract out the binary from the firmware. We bring that to some like standard distribution running on our virtual machine, for example, Linux for MIPS, Linux for ARM, Linux for ARM64. We copy, for example, HTTPD from firmware to our virtual machine and try to run it. So one easy way is that we run this target binary inside ch root on our virtual machine, right? So, however, we found that this one is not a very good way, because once we run the process inside ch root, we need to deal with many kind of issues. For example, we need to run debugger, then debugger need to handle like on kind of like complete things inside ch root. So we decided that we want to avoid ch root and you want to run everything as natively as possible. We decided that we copy the target binary to the virtual machine and run it. The first issue is that file not found. We could not run it. So you can see that on the screenshot, you can see that it cannot find bin bash, right? Actually, bin bash is always there, but you can see here it says that it cannot find the bin bash. So we found out that we run file on this bin bash and found that this one depends on one shared object file, which doesn't exist inside our virtual machine. So to solve this problem, we just copy this file from the firmware over to our virtual machine. So the first issue is not done yet, because once we copy the original binary to our virtual machine, we miss many dependencies, many standard program. For example, here you can see that we miss some standard process like PS or some many shared object files. So what we did is that we either copy the missing dependency from the firmware to our system, or we short link the existing shared object file from our virtual machine to the dependency that this binary is missing. Yeah, so after that we try to run, in this case HTTPD. And the program doesn't contain anything, but it just crashed. So we went on to investigate, and we found from SJ that it still misses some dependency, even it doesn't contain at all. So we run SJ on this binary, and we found all the missing dependency, and we short link the existing dependency to the right place. The next issue is that NVRAM. So after we fix all the missing dependency, it works, but after that, it stopped somewhere. So the reason is that usually the target binary is the binary you want to attack. When it runs, it tries to find the configuration. For example, HTTP, right? It tries to find some configuration for web server from the original firmware, which we do not have on our virtual machine. So the reason is that this target binary usually try to find the configuration into the NVRAM device, which is the device to store all the configuration of the target binary. So we try to solve this problem by, first one, we try to emulate the NVRAM device on our virtual machine to fix this problem. However, it was not easy because NVRAM device, they are different. Embedded system had different type NVRAM device, and NVRAM device, they do not have a standard, and usually they are even undocumented. So we gave up with this solution, and we need to find something else. So turn out that the target binary usually they do not directly contact the NVRAM device, but it contacts another process, which is the NVRAM process, and it sends the information request to this NVRAM process. And the NVRAM process in turn contacts the NVRAM device to get the information that this target binary wants. So the idea is that we do not emulate the NVRAM device, but emulate the NVRAM process, which is much easier. So how we did that? So usually the target binary, they connect to the NVRAM process via domain circuit, network domain circuit. So we build our own NVRAM process by writing something new from scratch. And this program bind to the domain circuit that this target binary wants. And listen for the request from the target binary and send back and forth all the information that this target binary wants. So it works pretty well. Another issue is that some wireless embedded system, they have some issues. So for example, when we run HTTPD from some network router on our virtual machine, it complains because it tries to configure the WLAN, the wireless LAN device. But it cannot find that because our virtual machine has no wireless device, right? So how to solve this one? we found a trick. We rename the standard ETH, the Ethernet 0, to WLAN 0, and it works. So that was a very nice trick, and it works very well. Okay, finally, if all of those solutions fail, what to do? The last one is that you get the target binary, we patch it, in case everything else fails. So we patch it so that the target binary can work in our virtual machine. But rarely we need to do this. Okay, so we show the first problem. We can copy the firmware, you can copy the target binary, and you can emulate that in our pretty good, pretty powerful virtual machine. So what to do next? How to fuzz it? So the idea is that because guided fuzzer depend on instrumentation, right? But we do not have the program. We do not have source code of the target binary. We only have the target binary to fuzz it. So we need a special dynamic instrumentation program framework so we can do the instrumentation. But unfortunately, on those public DPI you can find, it doesn't work very well on embedded system. It doesn't work on ARM, ARM64, MIPS, or PowerPC. So we had to build our own DPI. So we can do proper instrumentation for our fuzzer. So the concept behind the DPI is very simple. Dynamic binary instrumentation is a method of analyzing a binary at runtime by injecting extra instrumentation code into the program at runtime. So this extra code or instrumentation code are executed as a part of the original code. And one thing we need to be careful is that when we instrument the program, our extra code run inside that program, right? But we try best not to change the behavior of the program. Otherwise, we can break the program. Okay, so here's a simple diagram, so you can see how the DPI works. So we have original code here, like some code 1, 2, 3, 4. Now we want to instrument after 1 and after 3, right? So the idea is that we can inject our instrumentation code behind the code you want to instrument. So original we run 1, 2, 3, 4. Now after instrumentation we run 1 and our instrumentation code, and 2 and 3 and B, which is another instrumentation, and 4. So, but remember here that A and B should not change the behavior of the program. Okay, so there are two types of DPI techniques. The first one is just-in-time translation. The idea is that we transform the code, the original code, to something else, and we put this transformation code into a temporary buffer, and we do all the transformation here, and we run from the buffer, but not from the original place. So this JIT transformation works very well. It gives you the very good control on the code you execute. However, this CAP DPI is very heavy and very complicated to design and implement. So we look at another technique which is called hooking. Hooking is a very lightweight and very simple way to do instrumentation. So it's much easier to design and implement the hooking mechanism for DPI. One downside of hooking is that you have less control on code executed, because we need to know in advance where to instrument. Yeah, so there's some disadvantage of the hooking mechanism, but we decide to focus on hooking mechanism. So there are two type hooking techniques. The first one, very simple, is inline hooking. So the idea is that you want to instrument this original code. We want to run something after 1, run something after 3, right? So the idea is that we directly put the code inline after 1 and 3. And when you run everything. So the idea is that this inline hooking allow you to instrument anywhere. There's no limitation. However, you can see that one is still at the same place, right? But two, we need to move it. It's not at the original place anymore because it needs to be after A now, right? And the same thing, 3 is moved. 4 is moved. So all the code behind the instrumentation code is moved. And you see that this inline instrumentation is actually very complicated because we need to rewrite all the code after instrumentation. So we decided that we do not go with this hooking mechanism. So we look at another technique which is called detour hooking. So this one, you can see that we do not directly put our code behind the place you want to instrument, but we put it in another place. And the code you want to instrument, we just jump to our instrumentation code. But we do not put it directly after the code you want to instrument. So the idea is that you see that we branch to the instrumentation code. And actually in our framework, we use, we define some callback which will be executed when we reach here, and the callback will be run as an instrumentation code. And this detour technique, we need to use some intermediate, some temporary buffer to put our instrumented code inside. So this kind of buffer is called a chamberlain memory buffer. So compared to the inline instrumentation technique, the detour technique is limited because there are some places you cannot instrument using this technique. For example, if the basic block code is too small, you cannot override that basic block because you can override to the next basic block, right? However, this detour hooking is very easy to implement, very easy to design. So we decided to go with detour hooking techniques for our DPI. So yeah, so I will quickly introduce on the detour hooking mechanism here. So the idea is that we branch from the original instruction to our callback, right? But turn out that there are many ways to do that. The first one, you can jump to the trampoline. So here on the left side, you have the original code. Now we want to instrument here. So what we do is that we allocate our trampoline buffer. And we override this code with some code. First one, we say the context because jump can change the context in some CPU. And then you write one jump instruction here. And at runtime, we jump to our trampoline buffer. And first of all, we restore the context after we jump. So we come back to the original context. And we need to make a call to our callback, right? So before that, we save the context because call to callback can change the context. So we need to save the context here. And we make the call to the callback. And after that, when we return, we store the context. We restore the context, which can be changed here. And after that, we remember that we still need to run the original instruction, right? So the idea is that we can copy this instruction here and execute it after that. However, in fact, it doesn't always work because some instruction, for example, some relative instruction, they are very sensitive to the position in the memory. So when you copy those type instruction from here to here, it doesn't work anymore. So that means sometimes we need to relocate the instruction. Not always, but sometimes, before we can put it here. And after that, we jump back to the next code here. So you can see that instead of running the original code, we run this whole block. And we do our best not to change anything in the context of the CPU. So this is about jump to trampoline. Second one is that we do not jump to trampoline, but we jump to callback. So we can see that this mechanism, we do not use any trampoline buffer. So here, again, we save the context, override here, right? And we jump directly to the callback. And inside the callback, we restore the context. and we execute a relocate instruction and do something inside the callback, and we return to here, all right? So this technique, we do not use any Chamberlain buffer at all. So jump to Chamberlain buffer, jump to callback, but just another way to branch, which is cone. So here we have another technique, which is cone to Chamberlain. So you can see here that instead of jump, we do cone. We cone to the Chamberlain buffer, and everything else is the same. So we use cone to branch, not jump. Same thing, you can cone directly cone to callback, and here in this case, again, we do not use any Chamberlain buffer at all. So, yeah, looking at all those existing DBI when we did this research, we found that existing DBI, they work well, but they are not very suitable for our projects because they are very limited on platforms. So the idea is that actually for this DBI, I do not want to limit myself to embedded system, embedded platforms, but I want to have this DBI to work on all kind of platforms. I want to work for Windows, Mac, Linux, and everything else. But those existing DBIs, they have some limitation. For example, Vangreen doesn't work on Windows. Pin and Dynamorio, they do not work well on Mac, for example. The second issue is that they are limited on architecture supported, right? Pin doesn't work on anything but Intel CPU. Same thing for Dynamorio. But for our research, we want to have DBIs that work on all the embedded system, which can be ARM, ARM64, or MIS, or PowerPC. And of course, we want to support Intel as well. The other issue is that all those existing DBI, they provide some very easy and nicely framework. So people just use it to program their tools on top of those DBI. However, they hide many things inside, so we cannot customize it. For example, on those DBIs, they do not support all the 4 hooking mechanism I introduced before. The last issue is that because they hide many details, on those DBIs, they limit on the possibility to customize and optimize your tools on top of framework, on top of your DBI. So I came up with something myself. I built our own framework named Scorpio, and it has many features. It's kind of low-level framework, so you can build your tools on top of this framework. Scorpio is cross-platform. It works on all the platforms, on the operating system that I can try on. And it supports many CPUs. It supports Intel, ARM, ARM64, MIS, PowerPC, and Spark, and so on. It does all the 4 type instrumentation I introduced before. So you can choose whatever type instrumentation you want to do. And unlike many existing DBI you can find on the internet, you can find that those DBI, many of them only allow you to instrument at the function entry, but not anywhere after that. But Scorpio allows you to instrument anywhere in the program. It doesn't limit on the function entries at all. Okay, Scorpio is designed to be easy to use, but support own kind of optimization. And in some special cases, you can design very fast tool, which can be 100 times faster than existing DBI, which is important for the fuzzer, right? Yeah, here's how I build that. So I build some abstract layer to hide away all the details on the platforms, on the CPUs, and on the platforms and on the CPU come in the framework as a kind of plugin. So it support own kind of operating system and own kind of CPUs here. Yeah, a few things we need to care about when you build this one. First one, we're talking about cross-platform, right? For cross-platform, we need to think about how to deal with memory. So because different OS support different kind of interface to handle memory access. So one thing we need to do is that we need to allocate chamberlain buffer, right? And to allocate chamberlain buffer, we have different API on different OS to allocate memory. For example, on the Unix system, we use malloc, but on Windows, we use virtual malloc. Next thing we need to do is that we need to allocate chamberlain buffer to be read, write, and executable. And different OS have different way to set the permission to the memory. So for example, Unix, they use mprotect, Windows, they use virtual unlock. So I need to take care of everything like that. Next thing we need to do is that we need to write into the memory, to patch the code, right? To patch the code directly into the memory. And that depends on the OS as well. So first of all, we need to unprotect the memory, write to that, and reprotect again. And you can see that it's different on different OS. So for example, on Unix, Linux, Mac, they use mprotect function. On Windows, they use virtual protect for unprotect and reprotect memory. Okay, remember that we need to save, restore context when we build our instrumentation, right? And this one is not cross-platform, but cross-architecture, because each type CPU has different way to save memory, to save register, and restore memory, restore register. So remember that we try to keep the code size of the instrumentation as small as possible. So for example, on the Intel 32-bit, you can use this push AD to save all the register into the stack memory. And after that, we pop AD out. And we have as an instruction to save the E-flex registers. For other type CPU, it's not that easy because even Intel 64-bit or ARM, ARM64 or MIPS or PowerPC, there's no such simple instruction to save all the registers. So we did many kind of optimization here to keep the code small as possible and only save the registers that we really need to save. Yeah, and it's different. It depends on calling convention. Okay, we need to, in our instrumentation, we need to call the callback, right? When we call the callback, we need to pass the argument to the callback. And it depends. The passing argument to the callback, it depends on the CPU, and depends on architecture. So there are many details we need to take care. It depends on things you want to support. Yeah, some other details, and I think I should skip now because I do not have much time. Scratch register. Remember that we need to branch from the original place to the callback or to the chamberlain buffer, right? However, many CPUs, they do not allow it to branch to the indirect target in the memory. So that's why I need to have some temporary register to branch to the register, but not to branch to the memory. So we have some, we need to use some scratch register to calculate the branch target. Yeah, and it again depends on the CPUs. One more thing you need to do is that when you write to the memory, we override the code in the memory, we need to flush the instruction cache. So the CPU can be aware of the new code, right? So again, here it depends on the CPUs. For Intel, we do not need to do anything to flush the instruction cache. But for other CPU, we need to do that. And again, it depends on the CPU, depends on the OS. Yeah, so how we build Scorpio? Scorpio is built on top of two other frameworks of mine. It depends on Capstone to extract the code from the original place. So it knows the boundary where to override to. And remember that we need to rewrite the code, right? So I use another framework, which is Keystone here, to write the new code to the to relocate the code. So because Capstone and Keystone, they are cross-platform and cross-architecture, so that's why Scorpio built on top of that is also cross-platform and cross-architecture. Yeah, so actually this framework is kind of complicated because we want to support many things, we want to do own kind of optimization. Okay, so we have the DBI, right? So we can start to build our fuzzer. So how to do that? So our fuzzer, we build our fuzzer on top of AFL fuzzer, which is very good fuzzer for guided fuzzer. So the feature is that unlike AFL, we support binary only. Binary only target. So to do that, we use Scorpio, because Scorpio DBI allow you to instrument anywhere in the program, and it support own cap CPU. So you can build our fuzzer running on own cap CPU. We support selected binary fuzzing, which means that, so unlike other DBI like Pin or Dynamo Rio, when you use Pin or Dynamo Rio to instrument your program, it instrument program from start, right? There's no choice, but always instrumentation. But because Scorpio is using hooking mechanism, so you can choose where to instrument. So we only choose to instrument somewhere that we care about for our fuzzer. So our fuzzer also supports persistent mode in AFL. And besides that, it supports many other advanced techniques to make the fuzzer smarter, like simulated execution, or we combine many static analysis techniques to make our fuzzer better. Okay, the design is that our fuzzer is pure software based. We do not use any features from CPU to build this one. So it works everywhere in on-cap CPU, in on-cap environment. So because we do not rely on the actual hardware features. It works on the CPU, on the architecture, native compile on the embedded system, support binary, fast and quite stable. So how about the implementation? So as I said, we reuse AFL fuzzer. We do not change anything in the core of the AFL. So remember that the program, when you want to fuzz this one in AFL, you compile the source code, and the compiler, the special compiler, instrument this program for you, right? So now we do not have the source code. How we can still run on AFL? So the idea is that we just follow the mechanism of the instrumentation. In the case you have the source code. So you have source code, the compiler instruments the program, and we copy exactly the same thing. We instrument the target binary in the same way, and we use the same mechanism. So once our program is instrumented at the runtime, it connect to the fuzzer in the same way, exactly the same way. So in the other word, our fuzzer is compatible with AFL. So we do not change anything in the core of the AFL at all. So what we had to do is that we perform static analysis on the target binary before we build the fuzzer. So we locate where you want to focus fuzzing on. For example, usually we just focus on the parser code, right? So we reverse the program first and relocate the parser, and we focus on instrument only those areas. And we, of course, we use Scorpio to hook into the program at runtime. And as a result, our fuzzer is very fast. It runs at near native speed. Yeah, here's one example how we build the fuzzer for the network program like HTTP, like web server. So here's how it works. We run the target binary as a fuzzing target, like normal, right? And we only instrument the code handling the input from the client. So here we have client and server, right? You run the server inside the AFL, and we instrument all the code that handle the input sending from the client. Regarding the client, we put the client code inside the fork server loop of the AFL, and in turn, the client, when it runs, it initialize the client socket and connect to the server and send the input that is generated by AFL to the server. And it disconnects after that and repeat on the loop. Demo. Yeah, not sure I have time for demo, but just one screenshot. So we build our fuzzer and we try that on many embedded systems you can find. And yeah, we found many bugs, and some of them are very interesting. So like on this screenshot, you can see that this is a bug from some network router we found in China. And this bug, this device is very popular in China. So the bug we found here actually impacted, I think, like millions users in China. So, sorry, the screenshot is not very clear, but you can see that here we try to connect to the device with telnet. And of course, this device has no telnet open to the network, right? And then after that, we run our exploitation. And the exploitation connect to the web server running on this device, and it exploit and turn on the telnet. And after that, we connect to telnet server again on this device, and you can log in as a root. Okay, conclusion, and if you have time, we have some demo, some very quick demo. Okay, so we build our smart fuzzer, smart guided fuzzer for embedded system. We did that by emulating the firmware first, and we build fuzzer so it really cross-platform, cross-architecture. We support binary only. It's fast and stable. It found really impactful bugs in some real device. Questions, but before that, I think I have a few minutes. Can you run the video? Okay, so we build our fuzzer. You can really fast some binary. But because of the limited time, I cannot run this fuzzer on this demo for you on the real HTTP device. But here I run the fuzzer on some simple target binary on MIPS. So we see here that we try to we run our binary fuzzer on Linux MIPS, right? And this target is test2, which is very simple binary, just for demo. And test2 run with some input, and normally it do something. But in some special input, it can crash test2. So now I run this fuzzer with test2 on MIPS, and I try to find the inputs I can crash this one. So remember that we do not have the source code for test2. So what you can see here is that we run the fuzzer on MIPS virtual machine, and we do not have source code for test2. Yeah, so you see that after like 1 minute, we found one crash. So let's try to see if this crash can really crash the target binary. That's true or not. Yeah, so our fuzzer found one input, right? Now we try to run test2 with this input and see what happens. You see segmentation phone at the end. So yeah, the output that our fuzzer file can really crash the binary. And yeah, this is a very simple binary, but our fuzzer that can fast the real target like HTTP run exactly the same way. But it takes a lot more time, so I cannot show it here. Okay, so thank you.